Go ahead.
Cool. Sorry for being late. We just came from a demo presentation. So I'm going to be talking about graph databases. And has anyone used a graph database?
I don't think I've actually ever used one.
Okay. I have not, no.
Okay. Anyone heard of them before? Andrew shaking his head yes.
Just now.
Just now.
Yeah, I'm in that boat.
So I'm not exactly sure when I discovered them. I think it was in a tweet a year or two ago. I'm not sure. And I was like, what the heck is a graph database? And I looked at it and like, okay, looks interesting. And then recently, kind of in my own hobby projects, I found a really good use for it. And so I've done some work in them and just thought I would share kind of what they are. It seems to be an emerging trend, especially more recently. And so I guess it would just be good to share that knowledge, just so you kind of know what they are, know what they're used for, and you know, if a client ever talks about them, maybe they might not, there's specific use cases, but at least you'll have a little bit of knowledge. So that's, whenever I talk about graph databases to someone else, it's still really obscure. So people say, you know, what? Graph database? Did you say RAF database? No, it's not a RAF database. Did you say GRAF database? No, it's not a GRAF database. It's a graph database. So the visual behind me is kind of what the data would actually look like, and it's represented with nodes and relationships. So I took this screenshot from this guy. His name is Brendan Griffin, and he is an ace at scraping Wikipedia, using Wikipedia's APIs, and then running a whole bunch of processes to get Wikipedia information into a graph database, and then run some analysis, and then he generates all these really cool graphs. So the one I'm showing in the background is if you were to look at Wikipedia entries for programming languages, so this is actual Wikipedia. Inside Wikipedia, let's see, where is it? He's taking the influenced by and the influenced, and he's creating relationships to these other languages in Wikipedia using the influenced by and influenced data that's in Wikipedia. So, you know, he starts with a few languages, he runs his scripts, he creates nodes for each language, and if JavaScript, I'm on the JavaScript page, if JavaScript is influenced by Lua or Scheme, he'll draw a relationship in the database between those two languages, likewise influenced. So these are actually relationships that have direction, and we'll talk about that too. So he does a lot of that cool stuff. So this link is in the presentation, which I'll send out later. You should take a look at some of the stuff he does. So as you can see here, where is JavaScript? It's hiding behind this stupid thing, but JavaScript is well connected, which is great for us. Okay, so first of all, what's in a graph? So the word graph isn't like a two-dimensional or three-dimensional graph. We're not plotting points and lines in a two-dimensional space or three-dimensional space. So when I say the word graph, it's coming from an area of mathematics called graph theory. And a graph is an ordered pair. So G is a graph, and it contains V and E, where V is a set of vertices, which would be like the languages in our previous example, and E are the relationships between, so it says E is a list of two-element subsets of V. So if V was a list of the vertices A, B, C, D, E, F, E is two pairs or pairs of those. So this represents a relationship between A and B, a relationship between A and C, and a relationship between E and C. So this is the actual definition of a graph from graph theory and mathematics. It's mostly taken literally in the graph database implementation, but it actually adds on a whole bunch more stuff because within the nodes and within the actual relationships, you can add properties and data just like you would in any database. So you could see A node is as a document. And then the relationship, you could also store another document or properties or labels. So we'll talk more about that. So this would be an example if the relationships did not have direction. So 6 is related to 4, but there's no real direction, right? They're both related to each other. There's no arrow pointing from 6 to 4 or 4 to 6. So this is what's called an undirected graph. In a directed graph, the relationship has a direction. So B is pointing to C. Now what that means depends on how you're interpreting it. But there's lots of different, especially in math, there's lots of different algorithms and things you can do differently on a directed graph versus an undirected graph. For instance, network flow is a directed graph. And then there are weighted graphs, and that is where you put weights on the edges of relationships. So this would come into problems associated with solving minimum traversals. So maybe you're UPS and you have to send your drivers all around town, and there's 12 miles between city A and city C, 20 miles between C or here, or maybe this is the cost in gas. You can run algorithms on a weighted graph, a weighted directed graph, or undirected graph to find the cheapest route for your driver. And that is I think it's called there's lots of different ones, minimum spanning trees, minimum, I don't know. There's tons of problems associated with that are solved in the real world. Some major results from graph theory. In mathematics, the 4-color theorem is a major result. That's kind of fun. So the 4-color theorem was proven. Basically what it states is that any two-dimensional contiguous division can be colored in 4 colors so that no shared edge has the same color on both sides. So you'll never see green against green. No matter how complex this gets, this will always be able to be colored with 4 colors. And it was theorized, and everyone kind of thought it was true, and you can prove it by hand for 5 colors, but the proof for 4 colors required a proof of all the possible combinations, and then they used a computer to run through all those combinations. So it was one of the first big proofs that people accepted that was actually proved by exhaustive completion on a computer. So it's really interesting, and then this is, of course, used whenever you see a map of the United States. There's usually always 4 colors of the states, and so they're taking advantage of the 4-color theorem. I also like to have 4 colors of whiteboard markers on my whiteboard for this exact reason. I feel like it's just the right number of colors to have for all possible combinations. The stable marriage problem. This is a result from graph theory that allows you to optimize preferences. So this is used by medical schools for placement of residents. So the residents go interview at a bunch of schools, and the schools have their preferences for the students they want, and the students have preferences for the schools they want. And graph theory allows an optimization for the happiest possible match. So you may not get your best school, and the school may not get the best students, but overall, the compatibility is optimized. So if you had a whole bunch of people that had to marry each other, you could use this too to optimize the global marriage happiness. You may not have the best marriage, but globally, all marriages would be the happiest. Kuratowski's theorem for planar graphs. So a planar graph is a graph that can be drawn on 2-dimensional space and not have any edges intersect. And this is a pretty cool result. It's just interesting. Planar graphs are used in lots of applications. Not as exciting as the other ones. Modeling linear optimization, flight scheduling. So flight scheduling, you start to draw stuff like this. You have cost between cities. So the scheduling of airlines is a cost problem for the plane. And so the modeling of the costs for the routes is done using a graph and graph theory. And then this actually boils down to a set of constraints based on the graph, and then they add constraints for staffing and some other stuff. So the problem of solving how to schedule flights is just a huge problem that if it's not optimized would make airlines go out of business. And so huge result there that's used every day for things like bus and flight scheduling. So that's just a little background on graphs and the uses of graph theory. And then the people that use graphs in general, people in chemistry use graphs to model bonds between atoms. Social networks use graphs because all their data is in a big graph. You have friends who know this, who like this, who also knows this person who liked this. Computer networks and transportation, visualization in general, and then there's lots of graph-based data analytics like Google's PageRank algorithm. Early adopters of graph tech, the big three, Twitter, Facebook, Google, a lot of their data can be stored in a graph. In fact, most of it is graph-oriented with lots and lots of relationships between nodes. So we covered graphs. Any question on graphs in general?
I was going to say a good example I heard of the two different directed and indirected graphs is Facebook is indirected because when you become friends, it's mutual. And then Twitter is directed because you only follow.
You follow.
Yeah.
Oh, that's a good point.
So the updates go one way, but if you're on Facebook, you both get each other's updates.
Yeah, that's a good point. Cool. So a graph database. So the world is, social networking, all of these things, all this data. We used to just have a lot of flat tables of data, and relationships were there. In a relational database, you have a whole bunch of tables with a foreign key, and you can relate one table with another, and that's been done for a long time. But now the networks are getting really sophisticated. The amount of data and relationships are becoming huge, and that just doesn't work well in a relational database. And so it doesn't work well for two reasons. One, we'll see in a little bit, there's some performance benefits to using a graph database. And then also, if you're thinking about your data as a graph and you're modeling it as a graph, then your queries are semantically related to your graph. And so your queries and all your interactions and all your thinking and modeling is more aligned with how your data is. So rather than forcing a graph into a relational database, you have a nice tool if your data is naturally modeled and queried as a graph database. So nodes and relationships are first class. Local relationship-based queries are first class. So when I say local relationship-based, that means you have a starting point somewhere in the graph, and you start to traverse from a particular node out, and those perform really well. And we'll see that in a second. And we talked a little bit about this when you use a graph database. Your data model is just graphish. That doesn't necessarily mean it's a great candidate, but it's a great thing. It's actually, you really want your data to be graphish, otherwise you shouldn't be using a graph database. Most queries for your data are graphish, meaning you're trying to traverse through and utilize the many relationships that exist. And performance is really important to you. So there's some cases where you have a relational database and you can run a background process overnight and extract the data that you want from all the relationships. And so real-time performance of doing these types of traversals isn't important because you can just run a job and do it overnight and cache the results. But if you need real-time performance and you need to traverse through a lot of relationships very quickly, then this would be a good candidate for you. And then your queries shouldn't really require what's called a complete node scan in graph databases. So the nodes are indexed by their IDs. So it's a log 2n performance. It's very fast to find one node, but you don't really want to search through all your nodes. The graph database is most performant when you're going through relationships, and you have a starting place. So any questions on when you want to use one? Cool. All right, so let's talk a little bit about performance. So this is an excerpt from one of the guys that I think he might be the CEO of Neo4J, which is a graph database we're going to talk about. And this is kind of a problem that he illustrated why it's so much more beneficial in this use case to use a graph database over a relational database. So here's the problem. Given 1,000 users with an average of 50 friend relationships each, determine if one person is connected to another in 4 or fewer hops. So 4 or fewer hops means 4 relationships away. So a hop is a hop. And so in a relational database, you would have a table of users and a table of friends, which are connections, which would have the foreign keys for 2 users. So in order to go through and determine if one person is connected to another in 4 or fewer hops, you would have to do many, many, many joins many, many, many times. And so in a relational database, this can get a little bit unwieldy. And this is things that are common in applications like Facebook or Twitter. The ability to run these types of queries is very valuable. So let's take a look. Relational database can achieve the result in 2,000 milliseconds. And Jeff's just freaking out already. He's just like, it's crazy. So 2,000 milliseconds for a query is a long time. And for something that sounds so simple, that's quite a bit of time. So in a graph database, specifically Neo4J, that time reduces to 2 milliseconds, which is 1,000 times faster than a relational database. And it's not, it seems like magic, but it really is, you're trying to force a relational database to do something that it doesn't do well. And part of the reason, again, is there's so many joins and it has to do it so many times. But every time a relational database does a join, it has to allocate more memory. And when memory starts to become low, then all processes on any computer run slow. So let's see another example of performance. Let's up it from 1,000 users to 1,000,000 users. So that would be 1, 2, 3, 3 orders of magnitude bigger from 1,000 to 1,000,000?
I don't know.
I don't know.
Yeah, 3.
3? Okay, so 3 orders of magnitude bigger on the users. So you would think, well, a magnitude of 3, maybe we multiply the relational database's performance by 3, so we're thinking maybe now it's 6 seconds. We keep the number average of friends, so the number of relationships from each person, we'll keep it at an average of 50. And the relational database never completed, and they stopped it after 2 days. So I suspect that in this experiment, it was a memory problem. Because a relational database, they are still really fast, but as soon as they run out of memory, they're going to start swapping on disk, or who knows. So that just shows that it's probably not a good idea to attempt these types of things on a relational database, especially if you have a lot of data. And I'm pretty sure Facebook has at least 1,000,000 users.
That's some amazing latency.
Oh man, brutal. So you would kind of expect that the graph database would kind of go up. In the previous example, it was 1,000. So for 1,000,000 users, it was 2 milliseconds for 1,000. And for 1,000,000 users, still 2 milliseconds. And that is mind-boggling. I mean, it's crazy. Whoa. And again, when you first see that statistic, and it's got to be a little bit probably hyped up, because remember, this is coming from someone who's promoting their own database. But when you look at why it is so fast, you can see how it's possible that a relational database will croak while the graph database stays almost constant. So the reason why it's so fast in that type of a query is because of what's called constant, I forget the term, but here is, this is the generic term for it, but it has a constant neighbor lookup because we kept the constant of its neighbors at 50. So every time it has to hop, it can hop really fast, and it's always constant. But in a relational database, every time you want to look up a neighbor, it's log to n, where n isn't the number of neighbors, it's the number of people in your entire database. So because you have a constant neighbor lookup cost of 50, every time you need to hop, you're almost there instantly, because all you got to do is run through your index list of relationships, and then you're already at the next node. So you can traverse all possible relationships in your local neighborhood. They call a neighborhood is like a distance of 4 away. So in your neighborhood of distance of 4 away, you can get through that incredibly fast in a graph database. The only way the graph database would start to really take a crap is if your neighbors started to grow huge, because then you have the same problem in the relational database. You have to iterate through, and it starts to get bigger. But certainly, if you could still probably have several thousand relationships and still just beat the pants off a relational database. So awesome. So if you have a problem where you're doing these queries, you almost have to use a graph database, or you're really going to be in relational database heck. So some examples of graph databases that are out there in the market. There's OrientDB and Neo4J. Those are the two I'm going to talk about. There's lots of them that are out there. These are the two that seem to be the most widely supported and the most widely used in the web development sphere. I think there's some that are used in research, like in universities, that are a lot faster and are a little more directed at specific things. So comparison between these two, OrientDB and Neo4J. Neo4j is older, it's more mature. If you're importing a lot of data, it's faster. Neo4j can handle complex queries a lot simpler. The syntax ends up being a lot simpler than OrientDB. And distributed graph analysis. So there's people who have built open source libraries around doing analysis on your entire graph, like Google's PageRank algorithm. OrientDB, you have to set up quite a bit of manual stuff, and it's not distributed. So your whole database has to fit in memory for those to run. So they actually have a distributed package out there that I have a resource link. We'll talk about that at the end. Apparently, start-stop is faster on OrientDB. OrientDB's biggest advantage over Neo4j is that it actually is really good at storing documents like Mongo inside of their nodes. So Neo4j is most commonly used to just create the network and do analysis on the network, and then get your IDs from the nodes that you get from your query, and then go fetch the data from another database. Whereas in OrientDB, you get immediate access to that document. So if you want a document store and a graph database, it would be basically Neo4j equals OrientDB equals MongoDB plus Neo4j, if that makes sense. You can get the status of your database a little bit easier in OrientDB, and OrientDB comes with its own security like MySQL. Neo4j you'd have to set up behind a box that is trusted IP. Basically, you have to provide your own security around the database right now. I think they're working on security. Any questions there? Cool.
Sorry, I was on mute. Actually, can you talk a little bit more about the document storage and the mix of Neo4j and Mongo, and how would that be set up? I'm trying to wrap my head around that.
Yeah. So Neo4j, the nodes and relationships are objects that it stores, and you can put properties on the objects. So you could store a document on each node in Neo4j, but it isn't meant for it. So extracting the documents, there's not like a native support for like JSON documents. So you have to do a little bit of extra work to massage it and parse it and do all that good stuff. So, and they don't actually recommend to stick large documents in the nodes. There's not a huge performance hit. You can store, there's no like memory limitation, I would say, but Neo4j will run a lot faster, they say, because the amount of RAM that Neo4j can use significantly improves. So it's not that you can't do it in Neo4j, it's just OrientDB was built to be a document store. So I don't have all the specifics on exactly how much better OrientDB handles it, but I know that is one of the major differences between the two.
Okay, so if I have it right, you would use Neo4j to store all of your relationships, and then once you run your query to find out the document you wanted, you would could then just go over to Mongo and pull that one document for the actual information.
Exactly.
Is that okay?
Yeah. You put your Mongo document ID as a foreign key in your Neo4j nodes and relationships. Yeah.
Okay, cool. Thank you.
Yeah. And so on my side project, my personal hobby project, I'm doing that, and I'm doing that right now because I need this distributed graph analysis. And if I don't have it, I can't do what I want to do. If I did have it for OrientDB, I would probably consider switching because all my objects on the server, I have a node object, and it wraps two other classes, one to persist stuff in Mongo and one to persist stuff in Neo4j, and it's a pain in the ass. So if you think you're going to be using it more as a document store and you don't need the distributed graph analysis, or you don't need some of the stuff that Neo4j provides, then I would consider using OrientDB. I haven't tried it, but that would be a recommendation right now. So here's some dates, just some talking points here. So in 1970, Al Gore created the internet, and then MySQL popped up around 1995. So these are the initial release dates from Wikipedia. Neo4j came out in 2007, so it's been around, but it was used mostly in universities and for research. Nothing really in production, web applications, things like that. MongoDB came out in 2009. And if you notice, Neo4j plus MongoDB is OrientDB. This naturally followed. People started liking NoSQL, and so I think it was probably being developed in tandem, but this timeline seems to make sense. And then 2011, the D3 data visualization library, that was its first initial release. D3 is used in Neo4j's kind of console. So you can query in the console, and it'll show you the relationships using D3. So I think once this happened, and people you could visually see what a graph database is, I think things really took off. Because I was really surprised to see that it was 2007, and I only heard about it like a year or two ago. So I think the visualization piece helps get more people behind it and to understand it. So kind of interesting. Okay, so now we're going to talk a little bit about Neo4j specifically and its query language called Cipher. So as you can see, the creator really likes the Matrix movies. He took this from Matrix, and then 4J he just likes 4J, and then Cipher from the Matrix. So I put a link in the presentation, and I'll click it. So this is the site, and it's really easy to get this running. So you would do a community edition, and you'll get the download. I'm just going to cancel, and you can watch this nice video. And so this video will take you through exactly how to get it set up, and it's almost instant, and it works really great. So even if you just want to play around with it, you can get it up and running in like no time. So super easy to install.
You can also just pull Docker pull Neo4j.
Yeah, and yeah, they have a supported Docker image too, which is that's what I'm using. It's super nice, and you just spin it up. Okay, so this is what the Neo4j, they call it a browser, looks like, and it's kind of like a PHP MyAdmin. It's not super fully featured, but it gets kind of the point across, and it helps you kind of explore your data a little bit. So it uses a language called Cipher to make the queries, and these are what some queries looks like. So they really wanted it to be very like semantic, and they wanted it to be very visual. So when you create a node, the node is surrounded in parentheses to make it look like a circle. So a node is like a circle. So let's do some of these queries real quick. So I'm opening up the console. I'm just going to run a query to clear everything. And then I copy it over the create command. And here it says Created one node, statement executed in 10 milliseconds. So now I have a node in my graph database. If I want to find that node, I can do a match. So I want to match all, so n is a variable here. So once it grabs all nodes, I get access to n. So it's going to grab all nodes, and I'm going to return that variable. So you have the opportunity to perform a query, store the results in a variable, and then do something with them later in the query statement. So here I'm grabbing all nodes represented by n, and then I'm going to return all those nodes. And there it is. And they gave it its own internal ID right there. It's not recommended to use these as a UUID because Neo4j will reuse them as you delete them. So if you need to add your own ID, you would add it as a property, as like a foreign key. Okay, so now
hey John, like what are we actually looking at? Like there's like this dot.
Yep.
I mean, it's a node, but like what is? It seems like it has a it's got like a really big UI for that.
Yeah.
For that thing, right? For that record is how I would, I guess, think of it, or node.
Yeah. So this that's the really hard part about graph databases is visualizing a graph requires a lot of processing power, especially if you end up with a lot of nodes and edges. In D3, once you start hitting 1,000 elements in D3, it starts to die. So that's when, if you wanted to really visualize all your data, you would export your data into another tool. It's just tough to visualize. So the reason why it's so big is because this tool is meant to just traverse through your data a little bit at a time and maybe test some queries. That's a good point, though. You do have the option of looking at it as the data here. So I switched from graph to rows, and then you'll get to see the actual data within the nodes and relationships here. So this would probably be a more efficient way of looking at it if you were doing queries that are returning a lot of data, rather than trying to have D3 render a forced layout on 1,000 objects. That's a really good point. Let's see. So we created a node and we retrieved the node. Now what we want to do is we want to find a node by ID. So this node was created and it had an ID of 532. So this is what it looks like if you want to find one specifically. So you do a start, which means you're going to load something, either a relationship or a node, into a variable. So now you have access to this, and then I'm going to return it. And I get basically the same result, but that's the way you would look it up by ID. Okay. Okay, how about we delete all the nodes? So same thing, I'm going to match all nodes, and then now I have a reference to all nodes, and I'm going to delete all those nodes. Deleted. And then this is how you would delete a single node. I just deleted my node, so I won't do it, but you could go find that individual node and then delete it. So this kind of covers the really basics of just creating and finding nodes. Any questions there? Okay. Now let's talk about some of the data structures you can put inside your nodes. So one of the most valuable pieces in Neo4j is labels. This makes it incredibly powerful and flexible. So every node you can give one or more labels. So I could create a person node. I could create maybe a tweet node, and then I could point my person node with a relationship to the tweet node. And that relationship could have a label. Maybe the person actually tweeted that tweet, so the relationship would have a label of tweeted. Maybe he retweeted, so I would change the label from tweeted to retweeted. And you can see how quickly you can create queries where you could ask, give me all the tweets this user tweeted, or give me all the tweets this user retweeted, just by changing the labels on the relationships. So let's create a person. So the syntax, again, we're going to store this into a variable in, and it's colon label. If I wanted to add another label, I could do so. We'll just do person for now. And then I think it returns it. No, I got to go get it. So I'm going to get all nodes. And now you can see it's a different color. It makes colors based on the labels, and you can see down here that it has that person label. Has an ID, has no properties. I could create another node, and this node is going to have two labels, person and manager. So now I'm going to pull them both in. Now I have two nodes. You can see this one has manager and person, and this one just has person. Now let's find all the person nodes. So I'm going to match, I'm going to find all nodes that have a label of person, and I'm going to return all of them. And since both of them have the person label, I get 2. If I were to do the same thing, but they had to be a manager, I should only get 1. And there he is, my manager. This shows you how to delete using a label. It's really the same thing. All you got to do is get a hold of the nodes you want. We're going to get a hold of all the nodes that have the person label and then delete them. Now we should have deleted everybody. No one's left. Any question on labels?
How would you delete one label off? So you had one where they're person and manager. How would you remove the label?
Oh, actually remove a label?
So you can leave, so if you execute and delete all person nodes, it would still leave the manager one there.
Oh, yeah. And then, so you delete. Yeah, that is going to be out of my knowledge scope. I'm sure there's a way to do that. Yeah. So unfortunately, I'm still in the basics, but.
Because me, I would almost kind of consider that delete all person would be that, okay, kind of still leave it. If it's manager, just remove the label.
Right. So like delete all people except for managers, and then maybe update their labels. Yeah. Yeah, certainly possible. I am no expert. So that will be Jeff's next presentation. Okay, so that's labels. Nodes with labels. We did that already. Properties. So this is where it gets fun. And the syntax, again, they try to make it as semantic as possible. So again, the circles on the outside say this is a node. We're just having a variable here to store it for our queries. Here's the labels, space, and then your property list here. Now, this is kind of, I think, Mark, where it gets a little interesting, because if you did want to store a document, you would have to store the JSON stringified thing in here. So you'd have to stringify it, stick it in here on a property, and then pull it out. So it's not necessarily hard at all. But I think in OrientDB, it has a little bit more of a native feel. And you can throw whatever you want in here, man. You could throw in binary data. Whatever you want to throw in there, it'll take it. So let's create Bert. I could find him many ways now. I'm just going to grab all of them, but you could search him by label, and you can also search by his name too. And then you can see here, now he has a name property of Bert. If I look in the actual row data, now I can see the properties here. Can I type while doing UX for him? Hold on one second. Okay. Alrighty. Moving along, moving along. Alright. Relationships now. So we talked about nodes. Now we're going to get into relationships. One second. Five-ish, probably. Okay. So in order to create relationships, we need to have nodes between the relationships. So I'm going to clear everything and create a couple of nodes real quick. It's nice. This kind of keeps your history. You can go up and whatnot. So I'm going to delete everything. And now I'm going to create a node.
You might want to close your chat or something. The notifications are showing up there.
Yeah, sorry about that.
No, that's good.
So I'm going to create one node, and then I'm going to create another node. And I'm going to take a look at their IDs so that I can use them to create a relationship. So we have 537, 536, and 537. So I'm going to start at 536. I'm going to grab another node, 537. So you see here now when we use the start command, we're actually putting into a variable 2 different nodes. And then with those 2 in memory, we can run another command. So I'm going to grab N and M, and I am going to create a relationship. So the syntax for relationship, you see, it has a nice little arrow. So you actually draw a line in the query using the dash. Here's your data for the relationship in angled brackets, so you can distinguish between nodes and brackets, and then the direction of the relationship. So if I wanted to draw the arrow the other way, from M to N, I could do that. And that is pretty cool, because when you look at it, you know exactly what it's doing. Oops. How do I run this? 1, 2 lines. Okay, so now it's getting interesting. Now we have 2 nodes and a relationship. So in order to see all the nodes and the relationship, I need to get all of it. So I'm going to say, get me all the nodes that have some relationship to some other node. And it does its own kind of deduplication when you make this query, and then I'm going to return everything. If I can type. Oh, look at that. I created a child relationship. You see it shows up right here from 536 to 537. So now it's getting exciting. I can feel it over the phone. Okay. 2 quick points here. When you're creating relationships, you have to have a direction. So Neo4J forces you to have a direction on every relationship. You can ignore the direction while you're querying. So that's kind of nice. So you have to have an arrow when you create, but you don't have to use an arrow when you query. And then also, all relationships must be created with at least one relationship type, which is the label on the relationship. So in our query, you have to have an arrow for every relationship, and you have to have a label. Just blank relationships with no labels, I guess they consider it useless, because you need to know what that type of relationship is. So I guess it makes sense.
So on that, which is there a best practice or anything around, you know, if the relationship was sibling,
Mm-hmm.
you know, is it one is a sibling of another, of the next? Does it matter? You know, how does that actually play out when you're trying to? Is that what you're saying by querying? You know, that relationship would not matter.
Right. Yeah, that's a good point. So a sibling is kind of a bidirectional relationship, and Neo4j forces you to do one direction when you create the data. So in the database, it'll store it with the direction, but when you query it, you can ignore the direction. And we'll do an example of that. That's a great question. Does that answer your question, Mark?
Yeah, I mean, if you're using that same query, you know, with the child, that it implies that M is a child of N.
Yeah.
But if you're saying direction doesn't matter, is it just saying that N and M have a child relationship?
Oh, I see what you're saying. Yep. Yeah, so that is up to your interpretation.
Okay.
It's a little confusing, but just know that during the creation, every relationship is going to have a direction, but when you query, you can ignore the direction, which allows you to have that flexibility. So let's actually do an example of that. So let's create one more node. And I'm going to grab everything. Oh, I need to, since this query, I'm getting every node that has a relationship, I need to get a hold of just the node. So it doesn't return nodes because it's only returning nodes that have relationships in that query. Oops. So here now it's returning all the nodes. It kind of returns relationships just so that you can see the graph. It's kind of specific to the console. So this is 538. So let's do this. So we did one from 536 to 537. Now I'm going to do one from 536 to 538, and I'm going to change the direction. And now that it's connected, now we see this was the original node here, I think. So 538 was the new one. It's pointing here, and then this one's pointing out. So you could do match in. So now I'm using the same syntax. I'm going to match in. I want a relationship child pointing to another node. So let's do directional here. And then I want to return just the ones that it's pointing to. So I'm saying give me all the directed children from N. And so I get 1. If I remove the direction in the query, I get them both.
Okay, that makes sense.
Okay.
Thank you.
Yeah, it is kind of misleading, and I totally barfed on that for a while. And when I was coming up with, like, you don't really have a schema, but you kind of have a plan of the label types and the node types. And I tell you what, that really threw me for a loop. So great question. Okay, so now we've created relationships. We are moving along. Cipher relationships. Okay. You can create relationships. I won't run this query because I feel like I'm going to go long. I'm just talking so much information. But just so you can see what it looks like to create a relationship that has data inside of it, just like you put data inside of a node, you can put data inside of your relationship. And this is extremely helpful. So like Andrew was talking about Facebook or Twitter, let's say you actually create that friend relationship, you could store the date it happened. And you could provide an anniversary. Hey, you're friends with Jeff for 5 years, buy him a cake. So the actual metadata around this relationship proves to be extremely valuable when running some more complex queries. And then, of course, you can search. Oh, we already did that. Okay, so now I'm going to do a demo. This demo is built into this browser, this thing. So I'm going to start by clearing everything. Where's my super clear statement? There's one statement that deletes nodes and nodes with relationships. It's kind of a shortcut. Okay, so it's built into here. I'm going to go over it because I think it's really awesome and shows some of the power, and then you'll have seen it once, so if you have to go through it again, it'll make sense. So I want to, let's see, want to start learning, I think. Here we go. All right. Okay, so I'm going to use their movie graph example, which creates a database of actors and movies and their relationships. So let's see here. What's really nice is they show you the query that they're going to run, and you click it, it loads it up here, and then you can run it. So it's a nice, awesome way to do the tutorial. So this is what a bulk import file might look like. So maybe you're migrating some data from a relational database. Just like you can generate or export your MySQL database with just a list of SQL commands, this would be the equivalent of kind of a SQL dump. So here you see we're creating a whole bunch of, you can ignore the name, this is just a variable, the matrix, but this is the label. We're creating a label with some data. We're creating a node with person labels with some data, so we have movies and persons, and then at the end here you see that they're storing these references in the query. to then generate relationships between people and movies. So I'm going to click it, load it, play it. Now look at that. Now that's cool. There's actually a lot more in this database. So let's see if I can pull it out. Oops. Which one did I click on? No. This one. Movie graph. I got to keep this one on the screen. So we'll do match. And we're going to pull out everything here, all nodes and relationships. We don't have any unconnected nodes, so I'm not missing anything in this query. Should pull back everything. There we go. So it's pretty big. You can see the movies are colored in orange because they have the movie label. People are green. And if you hover over, I'm on Paul Bettany, James Cromwell. Let's see. As good as it gets, someone around here should be, who's in As Good as It Gets? James Brooks. Anyways, so this is a graphical representation of all those relationships between movies. It's pretty cool. And I will close that one. So next, through the tutorial, this is great stuff. So this is a way you can find Tom Hanks. There's Tom. You can find a movie. There's the movie. You can match on all the people. So here you get to see a little more advanced queries where you can do limits just like you would in MySQL or SQL. And then it lists out all the people. It looks like when it does a return here, I'm not exactly sure why it returned only the data and not the nodes. But that's a question for another time. And then this one's interesting. So find me all the nodes that are movies where the property of 90s release is greater than 1990 and 90s release is less than 2000. And then return me the title. So it's not returning the node, it's just returning the title. So we should see data. So this query is saying, give me all the movies that were released in the 90s. And it's going to return just the titles. So that's very almost SQL-ish, just to get that type of stuff. And it's very intuitive. Okay, now this kind of starts where the power of these databases really lies. So now this query says, match me a node. We're going to call it Tom internally. He's a person. His name is Tom Hanks. You need to then move from Tom Hanks and go to acted in relationships to nodes. So this guarantees that we're going to be following acted in relationships. Then we're going to store all those nodes as the variable Tom Hanks movies, and we're going to return Tom and the movies that he acted in. And Da Vinci Code, Green Mile, You've Got Mail, Joe versus the Volcano. Oh, look at this. I didn't ask for this. I think the console just gives me this. But you can see that he directed and acted in that thing you do. So that's kind of cool. You have two different relationships you can get to that thing you do from Tom Hanks. Let's see. Who directed Cloud Atlas? That's not as interesting. Here's one that's good. Now, this is really gets real fun. This one says, give me Tom Hanks co-actors. So you start with Tom. You find a movie here that he acted in. So this is a directed acted in. So this movie, M stands for all movies that Tom Hanks acted in. Then go find me all the co-actors that also acted in that movie, return co-actors.name. So it's weird. You have this like arrow pointing here and arrow pointing here, and it takes some time to get used to it, but this is semantically exactly what you want. Give me all this data, return me just the co-actors nodes with their names.
Is that the only? Can you only do two? I'm trying to think of any. That might be the only way you would possibly do it. Anyway.
Oh, multiple ways to get the same query.
I'm guessing, yeah. if you're trying to find an edge, then there's only 2 nodes possible. So never mind.
Yeah. I have run into cases where there's lots of ways to do the same query, for sure.
John, I got a quick question for you.
Yeah.
If you're going to use this database on a real project, what have you found to be the technology that leverages it the most? Is it sort of like a Node backend which plugs into this, or have you seen other languages sort of plug into this as well? I'm just curious.
Yeah, that's a great question. So it does have an HTTP exposure. So if you were to run it on your local machine, or like Andrew said, pull down the Docker image, it would expose an HTTPS or HTTP port, and then you could run HTTP requests against its internal HTTP service. And so you could use whatever you want, but people have written wrappers for pretty much every major language, Java, Node, what's that other one? Python. So yeah, very flexible. And I'm using the Node.js wrapper. I think they're still in development. So the Node.js one, I have to do a lot of massaging to generate the queries. Actually, I've had to write a few classes to generate the strings myself, because the library that they wrote doesn't support some of the advanced queries that I need. When they have wrappers, it's more like, get me this node, traverse here, then here, and sometimes I need something a little more advanced that can't be done using their libraries, and I have to generate the string myself. So I think that's true in a lot of languages. If you're doing advanced queries, at some point you're going to end up writing a pretty complex query and hard coding it. That answer your question?
Yeah. Yeah.
Cool. I won't run this query. All right, now here we go. This is the meat and potatoes of this whole demo for the movies. So let's pull this query up. This one says, movies and actors up to 4 hops away from Kevin Bacon. So this is the 6 degrees of separation, but we're saying 4 degrees of separation from Kevin Bacon. So give me all actors that are within a distance of 4 away from Kevin Bacon. So the query starts with a variable for storing Bacon. We find a person with the name of Kevin Bacon, and this is the interesting, super powerful part that I'm using, and that is variable length relationship hops. And it's just so badass. So this, notice I didn't name a type of relationship. You can do a type, and you can do 1 to 4 hops of that type, but this one is saying just give me any distance of any type of relationship. And then it stores all of those nodes that are within a distance of here, and then it returns them. It kind of returns them distinct, because it'll find like 8 different paths to the same person, and you need to actually reduce those paths down, so you actually do a distinct call on that, so you don't get duplicate names. There's no way around that. If you were doing it in a relational database or graph database, you have to search all relationships and paths, and you end up with repeat paths, but then you end up reducing them. So we'll run this. And this is everybody who's connected to Kevin Bacon within 4 hops. So Kevin Bacon is right here. And so every green node you see is within a distance of 4 from this guy. And that's awesome. And having that type of power and query to run that fast is just huge for certain types of applications.
Hey, John, instead of having the numbers output, could you make it more readable and have like the actual names, the labels, instead of the IDs?
Yeah, that's a great question. I don't know what the heck it's doing. Maybe it's when you use the key of title. This one's using a key of name.
Yeah.
I think I'd have to look into that.
I'm sure you can. I was just curious.
Yeah, that's a good point. I'm sure there's a way. So that's awesome. But you can already, my computer, I don't know if you can hear it, but it's already humming, because D3 is running, a forced layout on quite a few people here. Kevin Bacon connected to a lot of people. So I'll let that, there's one more query, but we'll let that conclude. Well, let's run it. Another powerful, there's some functions that are built in. So shortest path is one of those functions. So this is saying, give me the shortest path to Meg Ryan. So find me all the paths to Meg Ryan, but give me the shortest one. Oops. And the shortest one, here's Kevin Bacon. He acted in Apollo 13, and Tom Hanks also acted in Apollo 13, who also acted in You've Got Mail, which also starred Meg Ryan. So that's the shortest path to get from Kevin Bacon to Meg Ryan, from Apollo 13 to You've Got Mail. That's pretty cool. And it's very semantic. I mean, when you read this query, I'll put it back up there. Give me the shortest path. So this will return, this query here returns a whole bunch of paths. And variable length, so any distance, and then give me the shortest one. It's pretty cool. Okay. So that concludes the demo. Again, that's really this built into this browser, so they have several demos that you can run through to help you understand the queries and what the graph database can do. All right, moving along. Common implementations that people are using right now in production. Recommendation engines. That's the #1 use of graph databases right now. So when you store a purchase, so let's say you're on Amazon, and Matt Palazzati buys a really nice bottle of scotch from Amazon. And then he also bought maybe the whole set of DVDs for Mad Men. So he bought Scotch and Mad Men. And then you go in, so now there's a relationship in Amazon's graph database, and the node is Matt as a person, and the items, there's 2 item nodes, and Matt has a purchased relationship between both of those. So now I go onto Amazon and I purchase scotch. Well, now I can traverse the database and find other people who purchase scotch from the relationships, and then look at what else they bought. And then it'll recommend that I also buy Mad Men. And it's done in a way that is just super fast. So recommendation engines is a huge, awesome application of graph databases. Fraud detection is another one. This one's pretty big. I don't know all the details of how the graph database is used, but this is huge for graph databases. And then similar to recommendations, this is what I'm using it for in my internal application. I'm using it to search for icons. So I'll open up the database for my hobby project. So this is another instance of Neo4J running in a Docker image. And I will say, give me everything. Oh, whoa. Super lag. Sorry about that. Oh, that's really terrible. So I'm going to show everything that's in my database. Okay, let's see. I need to find a particular node. Can I move this thing? Yeah, get out of here. Let's see. Okay. Here's one. I'm going to pull this one aside. And here's one. So I'm trying to group these visually for you so this makes sense. Okay, so here you see I have what I'm calling a sensory node, and that represents an icon that's in my system. So I have 3 icons here. And this icon has multiple keywords. So on the bottom of my screen you see that this icon has keywords brain, AI, artificial intelligence, wiring, neuroscience. This one has the same set of keywords. And this one down here is a little bit different. This one has graph, brain, network, connected nodes, linked neighbors. Okay, so different sets of keywords, but you notice that they both share the word brain. So in my graph database, I've created an icon recommendation engine. So what I do is I create what I'm calling an ontology group, which has all of a set of keywords, and then it creates an ontology for each keyword. So this ontology is for brain, AI, artificial intelligence, wiring, neuroscience. then I also generate an ontology for each of those words. So this is for AI, here's for artificial intelligence, here's for neuroscience, etc. So this one has brain in it, so it creates a brain node. But this one also has brain. So you see that these ontology groups are connected by the keyword brain. Does that make sense? And these icons are directly tied to their ontology groups. So when I create an icon in my system, I have keywords. I immediately generate an ontology group for those keywords. Then I generate the ontology nodes so that when I create a new one, these relationships start to form naturally, almost organically. So if I were to ingest a new icon with new keywords, you could see this process. The green thing would show up. I would generate an orange one that stores all the keywords. And then I would blossom out into each of the ontologies, and then I would draw relationships. First, I would check for the existence of that ontology node, and if it existed, I would draw a relationship right across. So it just grows organically. So how this works in my system is the difference here is they share brain, but this one has the word network in it that the other ones don't. But they're very closely related. I mean, look how close. This is only one hop away. It seems reasonable that if someone searches for the word network, I should go find other icons that are within a certain distance, and then also give that to the user. So I'm going to search for the word network. Oh, that's the wrong screen. Search for the word network. And you can see this is the icon that had network. It also had brain, and it brought in the other two automatically. So this is like my own icon suggestion engine. Does that make sense? So pretty cool and very powerful. So as I put more icons in, I already have the code written to generate the connections. So as my icon library grows, it's just naturally going to just form. And things are going to get auto-suggested based on distance. And as it grows, I can change, how far away do I want to include? Maybe if it's 7 hops away, maybe that's irrelevant. Maybe I cut it down to 2 or 3 hops away to make them, more relevant. So suggestion engines are huge for graph databases. Okay, big data example. So here is this guy, John Swain, who I'm following on Twitter. He tweeted out an article recently about how he created an analysis of influencers within Twitter around the topics of big data. And he ended up using a graph database to do a lot of this work and then create this visual and have all this data. So you can see these are the Twitter handles of the most influential people on Twitter for the topic of big data. And this, I mean, if I had this tool, I'd be a millionaire because you could sell this data to politicians. I mean, I don't know. I wish I was this person because I'd be rich right now. So he has all this set up in a process, and it's really complicated. But what he does is he decides what words in Twitter constitute a big data tweet. So he comes up with words like big data, Apache Spark, all that stuff. So he has this whole thing about how he comes up with the words. So you can see the words that he's choosing. Machine learning. So he has his own logic. Then he goes out to Twitter from the fire hose, pulls down every tweet within a specific time frame that has those keywords, and then using all the Twitter data, you can draw relationships between tweets and people and retweets and all of that stuff. So you get all this huge network of data. So you see here, you naturally can create relationships, contains about these natural relationships that are already in Twitter. He transports into a graph database. He deletes some of the garbage, and he does a lot of work. You can see here to reduce noise. There's lots of computers that automatically tweet, and he had to come up with a way to identify those. He did some of that visually, just by looking at the graph. He could identify some people that were probably computers, or some people he could actually just trim out because it's not relevant. So just having a visual of that data really helped him reduce the noise and clean up the data. And then when it's all done, you just have this. He runs, okay, yeah, so when it's all done, then he runs Google's PageRank algorithm on the graph database, and that gives you the PageRank for every person. And that basically tells you who your big influencers are. And it's just incredible. So an awesome use of graph databases and graphs in general. I really, really like this example.
What does he do with that info? Spam them?
Well, you certainly could. So I was actually talking with Jason Brown about this, and let's say I was a PR person for a celebrity. I could actually strategically think about how influential I want my client to be in different areas on social media. So maybe I want my client, maybe he's writing a book about neuroscience. So now I pulled all the data for neuroscience. I find all the influential people on Twitter around neuroscience, and I start setting up my Twitter account to follow them. I try to get them to follow me, and I try to get them to retweet my stuff. Because if they're influential, the stuff's going to propagate like wildfire. So PR people, lobbyists, politicians, could you imagine having this tool running for president?
Yeah, that's awesome.
Yeah. So, and it's all very performant in the graph database. Another thing I'll say is I was talking about graph analytics, and it's something that I really wanted, so I chose Neo4J. The Google PageRank algorithm, that's one graph analytic you can run to get the PageRank of every node in the network. There's many others that you can run that are extremely valuable. So there's something called, there's many words, some people call it a choke point. But if you had like a whole bunch of people over here on one side, a whole bunch of people in relationships on the other side, but maybe one person in the middle that connects them all, that guy is basically a choke point for flow of information across the whole network. So you can think of those people in terms of their personalities, but they have a different role in Twitter. Influencers have strong connections across the whole network and short distance between everyone in the network. And then people at choke points have a special role because they're the people that take information from one side, propagate it to the other. So they have like a lot of control, and it's super, super interesting. I don't know all the implications, but it's really cool.
So I could see how you could use this to study the market too.
Oh yeah.
If you could scrape data for the stock market and see which is best performing stocks over time.
Probably. Yeah.
Or I think Jason, you probably talked to Jason Brown about this. There are some guys who use big data to analyze. It's either DraftKings or the FanDuel. They analyze NFL data.
Yeah.
And they place bids and bets based off the best performing combinations of teams, and they're making 20% on their money.
Sure.
Pretty cool though, huh?
It is cool.
So I'll tell you what I want. This is what an idea I had the other day. I want to not do sprint planning anymore because I want it to figure out how good everybody is at whatever.
There you go.
Whatever types of tasks they have.
Just label
based on
them.
keywords, yeah.
Ooh.
And then just pack it in. Like, give me my 40 hours a week and I'm done.
Oh, yeah. Some AI. That'd be slick.
So is there an idea of what the larger or largest of these graph databases are? I'm sure Twitter, Facebook, and the NSA are probably like somewhat tied. But is there any idea of like how big these things can actually get?
So for the databases I presented on OrientDB and Neo4j, I think OrientDB clusters and Neo4j also clusters. You have to buy the Enterprise Edition, but I don't think there's a limit on how big it can be right now. I am guessing that Facebook, Twitter, and NSA probably have their own internal tool that they've built. I don't know that they're using any of the databases that I've discussed. But yeah, they could get huge. and that's that PageRank algorithm. It runs on Apache Spark. It spins up multiple. It makes an Apache Spark cluster, and then it grabs pieces of the graph, one piece at a time, and it runs the PageRank algorithm on its different pieces, and then communicates with each other to tie up all the loose ends, and then repopulates the database with the PageRank over time. It takes time, especially on a large database. So I don't know a really good answer to your question, but I do know that they can cluster and can scale. I don't know how well though.
Okay.
So what's next? We've covered a lot. What's next? Wow, this lag is really bad. There it is. What's next is go explore and traverse using graph databases. I've had some resources here. I put a link to this book. It's actually a college textbook on graph theory, and it's free. You can print it out as a PDF, but it is like awesome, and you don't have to know anything about math to read this book. It's super interesting. There's a link here to common Cipher queries that people use, like how to clear all your data real quickly. This is a link to that big data graph analytics tool that I'm using. This guy, Kenny Bastani, he wrote it himself, and then Neo4J acquired it. I don't think they purchased it. He just let them open source it. So they're actually managing this now. So it's an actual tool that Neo4J supports. A link to the big data. Oh, this is a repeat of this. Oh, no, that's not true. This is the college textbook. This is a graph database book, an introduction to graph databases in Neo4j that's excellent, and it's free, and it's provided by Neo4j when you download Neo4j, and it's super helpful. I actually found Highlight.js, so the reveal slideshow stuff. The queries were in Cipher, and I actually found a Highlight.js plugin for Cipher queries, so I put the link there. And then this was, I think, related to one of Matt's questions. It's really tough to see a huge network of data using D3, so I think this guy generated this graphic using something that's pretty popular called Gephi. I think it's Java, I think, but it can handle huge graphs, and you can interact with them. It's actually interactive. Oh, graphics. Okay. So this would be a tool you would use if you really wanted to visualize all of your data at once. But it is interactive, so when you highlight a node, yeah, you can get in there. Oops. So those resources in there, I'll email out this presentation, and that's it. I get a really kind of lukewarm Hermione clap. So any questions? Oh. The Harry Potter over there too? I just finished all the Harry Potter movies recently, so I'm like on a Harry Potter kick.
John, how much time do you have? I mean, you're doing graphing, you're watching all the Harry Potter movies, you know? Jeez.
Yeah, man.
Kids, man. You gotta have some kids. I gotta pull you down with the rest of us. Time management. That's amazing.
I mean, the graph stuff has been, I've been doing it for a couple of years now. So it was kind of nice to present on something, in and out for the most part.
What do you use it for, personally?
Well, I showed one demo of that icon stuff. This is my side project where I need to be able for a user to search for an icon, but not come up with empty results. So a little more, I'm not going to tell you everything about it because it's top secret, but this part, what actually happens is when I ingest an icon, the icon comes with a set of keywords, and I index those set of keywords in Elasticsearch. So I'm hitting Elasticsearch because Elasticsearch is super fast for text searches and gives you the flexibility for natural language processing. So if I search for the word networks, plural, I get the same results because Elasticsearch treats networks and network as the same. In fact, if I do networking, it keeps a base word of network. So I can search for all types of words, and it gives me back the bases. So then once I get that, when I index it, I also index the node IDs in my graph database. So when I get a hit, I get the node ID from my graph database, and then I traverse my graph database for the recommended other icons. And this isn't like magic. This is exactly how every single recommendation on the planet works. If they're in general, I mean, they may not be using a graph database, but this is kind of the process.
So are you writing a service to always return you an icon?
That's one part of my application.
Oh, okay.
Yeah.
Okay.
But what's interesting is, I have this recommendation engine on. So here's kind of another interesting thing. You could have a graph database, and you could have sections of the graph that don't touch. Like you could have like maybe you sucked in some Twitter data, and it goes into the graph database. Maybe you suck in some Facebook data, it goes into the graph database, but there's no relationships between that data. You could do that, right? So like I have a whole service just with icons and these ontologies or keywords. It could be completely separate from the rest of my system and still be using the same graph database. What becomes really interesting is when you start to tie relationships between those big groups. I mean, imagine if you had all the Twitter data and Facebook data. You could traverse through multiple social network data very fast. It could get really interesting. Cool. Well, if there's no other questions, I think I'm all done. So I guess feedback.
Anybody else have any questions?